Okay, so in this lesson, we would like to address a few things which we feel like students could have encountered from the tutorial. Assuming first that you already have gone through the slides where we talked about the laws of limits or properties of limits. You have already used some of them in the tutorial, and you use the direct method, where we say with a direct method, if you have the limit Sx goes to a point A of f of x, we can directly substitute A for x, then we have f of A. So this is I'm sure at this stage people are very clear of this one. But this is not always the case. That's the problem. So this is not always the case, as we have seen in the tutorial. In some cases, some work needs to be done before direct substitution. So in some cases, some work needs to be done before direct substitution. Before direct substitution. E.g., so let's look at a couple of examples with different cases. So let's start with example 1 to try to just give you an idea of what may be expected. So suppose you want to evaluate the limit as x goes to 2 of x squared plus 4x minus 12, and then it's divided by x squared minus 2x. So in this case, one thing that you see, if you are trying to do direct substitution, if you try direct substitution, you end up with 0 over 0. That means in the numerator you get 0. When you plug in 2, in the denominator you also get 0. That's really a problem. And once you have this 0 over 0, we normally say this is an indeterminate form. You will see a lot of indeterminate form as we go along with calculus, but let's introduce this first one. So this is an indeterminate form. So that means you need to do a little bit of work before you do the direct substitution. One of the things to try is try to factorize in this case, because you can see that the top and the bottom can be factorized. So let's try, and then let's see the limit as x goes to 2 of x squared plus 4x minus 12 being divided by x squared minus 2x, and then if we try to factor that, you should get x minus 2 and x plus 6 on the numerator. In the denominator, you can factor x out, and then you are left with x minus 2. Beautiful. And you can see now it looks much better than before, because you can see some two terms which are likely to cancel out. And in this case, we are safe to cancel out because we assume that x is different from 2. So we assume that x is different from 2. So if we do that, we have the limit as x goes to 2, then and on the numerator you're left with just x plus 6 being divided by x. And then you are ready now to substitute. There's no problem, we can plug in 2, so that means now we can have 2 plus 6 at the numerator. In the denominator we have 2, and then we end up with 8 divided by 2, which is nothing but 4. Beautiful. So this is one of the examples where you meet 0 over 0, and you need to do a little bit of work before you can get to the answer. That's one example. But now let's look at another example, probably with a different case. So let's look at number 2, which is the second example, where we have the limit as h goes to 0 in this case. Then you have 2 into minus 3 plus h squared minus 18 being divided by h. Again, if we try here in this case, you can see that we are still having the indeterminate form of 0 over 0. You put h to be 0 here, then you have minus 3 squared, which is 9. 9 times 2 is 18. 18 minus 18 is 0. In the numerator we have 0. So we need to do a little bit of work, but in this case it's different from the previous one. Remember, on the previous example we had to factorize. Here we have to expand. So it says somehow you need to be flexible to work with different challenges. That means the more you get used to with solving many of them, the more you'll be used what is needed for each case. So here you need to expand a little bit here where you have minus 3 plus h the whole thing squared. So if you do that, you have 2 into 9 minus 6h plus h squared. Then you still have minus 18, then you still have to divide by h. So if we can see where we expand or factorize, I skip some steps because I know you are a very good student from algebra M1511, or a prerequisite for this course. So you should be good at that. Otherwise, go back to the basics and then try to work them alone and then catch up. So in this case, then you go again. You have the limit as h goes to 0. If we simplify again, you have 18 minus 12 h plus h squared minus 18. It still need to be divided by h. So if you do that, eventually you have the limit as h goes to 0. Then you have minus 12 h plus h squared over h. So this is what you have, which straight away you can be able to factor h outside on the numerator. So you have lim as h goes to 0 of h. Then you can start with the positive term, where you have h. Oh, you still have 2h. You have 2h. 2 here. Remember, we forgot 2 when we multiply by 2 inside. We had 18 for 9 times 2, and then 6 times 2 is 12. Then we had 2 times h squared, which is 2h squared. So I left out the 2. So here we have 2h, then you have minus 12. Then it still need to be divided by h. And the h cancels. Now you're left with the lim as h goes to 0 of 2h minus 12. Now you are ready to substitute. You plug in h to be 0, you are left with minus 12. So this is another example now where we see that you need to a little bit brush your algebra and then bring it back, because it's really needed here in cases like this. So this is one of the cases that probably you have met or you're going to meet most of the time as you work out these problems. So let's look at the last one, the third and the last one. The third and the last one. So the third and the last one, let's see. So that's example 3. Example number 3. So example number 3 is of this nature. You have the limit as t goes to, oh, I'm a 0 guy now. I'm trying to say as t goes to 4, and then you have t minus root of 3t plus 4. And then you have 4 minus t. So, again, if you try to plug in 4 here, you are back to indeterminate form, 0 over 0. But a different technique to apply this time. Once you involve the square root of something, there is a suspicion that you might need to rationalize, especially if you cannot factor. So in this case, you can try to factor, but I feel like you will work very, very hard to get there. So let's try straight away to rationalize and target the term with the square root, rationalize the numerator. So straight away, let's try to rationalize as another technique to try to solve this. So we rationalize the numerator. We have t minus root of 3t plus 4 over 4 minus t, and then you multiply that by t plus root of 3t plus 4. I'm sure you're good at rationalizing, that's why I'm just writing the terms t plus 3t plus 4. We have done that a lot in the algebra. So this is what we have. And if you do that, immediately what you pick from the numerator, you have two expressions which are multiplying. T minus root of 3t plus 4, and then multiplied by t plus root of 3t plus 4. This calls for a difference of 2 squares. Please remember difference of two squares. So now it means you have t as that goes to 0. When you expand the 2, you have t squared minus 3t plus 4, all being divided by 4 minus t, which is multiplied by t plus 3t plus 4. If you don't see the issue of difference of two squares here, you don't need to worry. Just expand the two expressions. Just expand these two brackets, the top part, and then you should be able to get what we have here. Should be able to get what we have here. So now let's see where it takes us. So looking at the top, if we try to go to the next step, we have limit as t goes to 4, and then we have t squared minus 3t minus 4 all over 4 minus t multiplied by t plus square root of 3t plus 4. We thought here we'll get to something quite simpler, but still, after rationalizing, somehow it still looks a little bit weird that we are still not able to substitute immediately. So and when you look at the numerator, it's some kind of expression that you might have a feeling that if we factor the numerator, probably that the expression in the numerator, which is giving us a problem when we try to substitute 4 for t, it may cancel out. Let's try and do that and see. That's the feeling that we have. So if we factor the numerator as t goes to 4, what do you get in the numerator when you try to factor? You get t minus 4 into t plus 1. And in the denominator, you still have the two expressions, 4 minus t into t plus root of 3t plus 4. So you still have something like that, and you are tempted to do cancellation at this stage, and you find that numerator you have t minus 4, denominator you have 4 minus t. So there is a minus sign that need to be factored before. So either you factor the numerator or denominator so that you have t minus 4, both numerator and denominator. So let's factor the numerator. In fact, we can put that minus completely outside, so we can have minus the lim as t goes to 4, then on the numerator now we have 4 minus t, and then we still have t plus 1. Denominator, you didn't do anything, so you have 4 minus t, and you have t plus root of 3t plus 4. And then now you are ready to cancel. The two terms can cancel now. They look identical. So now you can have minus the limit as t goes to 4. The numerator you're left with t plus 1 over, in the denominator you have t plus, you have t, and the denominator you have t plus square root of 3t plus 4. And you can see now you are ready to substitute now. So it tells one thing, that you need all these techniques of algebra to manipulate these expressions before we can apply what we know about the limits. So you need all of them at your fingertips. So now that we are ready to substitute, let's substitute. once you substitute, be careful. The moment you just substitute the limit, once you substitute 4 for the limit for t plus 1, you no longer bring the limit, the term limit, before here. So you are left with just minus here. Don't put the limit because now you are substituting. That means you are using the value of the limit. So you have 4 plus square root of 3 into 4 plus 4. So we have plugged in 4 for t. And then once we substitute, remember, leave the limit because now you have used the limit. So don't plug in and then still carry the limit with you. So you simplify the top part, you get minus 5, the bottom part over 8. This is what you get for your limit. Beautiful, beautiful. So this is what you get as your answer. So what's the message with the lesson that we have learned today? We have learned that when we have 0 over 0, it's difficult to substitute directly. And you need to do some work first before you do direct substitution. That's one thing you learn. And another thing that you learn is that as you do your work, there are different techniques to apply. In the first case, with the first example, we found that we had to factorize before we can simplify our expression, then we start substituting. In the second case, we had to expand our expression before we start doing the substitution. In the last case, we had to do rationalizing. And not only the rationalizing, after rationalizing, we found that the expression still looks a little bit complex. So we applied 2 of them. We had to factorize also. So you can see that you may need all these techniques at your fingertips as you work through these problems. So please use whatever you have, all the tools that we have to evaluate the limits. And with that, I think that will help you. So one thing to mention before we stop is that if we have 0 over 0, we classify that as an indeterminate form, and then we need to do a little bit of work before we can do the substitution straight away. But you may have some value which is different from 0 but divided by 0. Remember we dealt with that before, where we could find, where we say if the denominator approaches 0, now it calls for a vertical asymptote, which will be vertical asymptote, and the limit, most of the time it will either approach plus infinity or minus infinity. So that means the numerator is a value, the denominator is it approaches 0. There, the limit might go to plus infinity or minus infinity, which will classify as our vertical asymptote. We may have another case where you have the numerator being 0, but the denominator is different from 0. In that case, the limit is 0. No problem. You don't need to think about indeterminate form. If the denominator is different from 0, it's a value which is finite, which is different from 0, and then the numerator is 0. The denominator is some value which is different from 0 but finite, then definitely the limit is 0. That's one thing to mention. Be careful of those cases. So that's it. So let's stop here.